This is module 2 of chapter 2. In this module, we shall discuss about Newton's method, Newton's polynomial interpolation methods. In first module of chapter 2, we have mentioned or we have deduced the Lagrange interpolation method. In that method contains lot of arithmetic calculation, but in Newton's method, the number of calculation is very less compared to the Lagrange method, and in these methods we have assumed that the given points are equal space. So, three different type of Newton's methods we shall describe in this module. These are Newton's forward interpolation polynomial, Newton's backward interpolation polynomial, and Newton divided difference interpolation polynomial. But the first two interpolation polynomial takes equal space argument. The third method is known as Newton divided difference interpolation method. In this method, the arguments may or may not be equal space. But one interesting thing is that using this method, we can derive the Newton's forward interpolation formula, Newton backward interpolation formula, and also the Lagrange interpolation formula. Now, we shall discuss this method one by one in next slides. First, we consider Newton forward difference interpolation formula. So, in this case, we assume that a table of values of x and y are given. The values of x are denoted by x0, x1 up to xn, and the values of y are y0, y1 up to yn, where xi equal to x0 plus ih, where I equal to 0 to n. This condition actually implies that the arguments are equi-space. So, for this assumption, we construct a polynomial phi x whose degree not more than n, and that must satisfy the condition yi equal to phi of xi for all I equal to 0 to n. So, this is the condition for any interpolating polynomial. Now, the main problem is from this table we have to compute the value of y when the value of x, say x dash, is given, that one mentioned by red color in the table. So, this is the problem. That means, when the values of x is at the beginning of the table, then we use the Newton's forward interpolation formula. Now, we describe the Newton forward difference interpolation formula. Let the polynomial phi x be the following form: phi x equal to a0, that means the constant term a0, then a1 into x plus x0, this is the first degree term, plus a2 x minus x0 into x minus x1, this is second degree term, and so on. Lastly, a n into x minus x0 into x minus x1 up to x minus x n minus 1. Note that the degree of the last term is n, where a0, a1, a2 up to a n are the constant, and their values are to be determined using the condition yi equal to phi of xi. This condition must satisfied by the interpolating polynomial phi x. Now, to find the values of this constant, first we substitute x equal to xi in 1 according to the order I equal to 0, 1, 2 up to n. When x equal to x0, then phi x0 equal to a0, that means all other terms contains the factor x minus x0 when x equal to x0. So, the remaining terms are zeros. Then a0 equal to y0, this is the first value of the first constant a0. Then we substitute x equal to x1, then from the polynomial 1 we have phi x1 equal to a0 plus a1 into x1 minus x0, or y1 equal to y0 plus a1 h, because phi x1 equal to y1. After simplification we get a1 equal to y1 minus y0 by h, and this is equal to delta y0 by h. Delta y0 means the first order forward difference operator applied on y0. When x equal to x2, then we get the value of a2, and that one is equal to y2 minus 2 y1 plus y0 whole divided by factorial 2 h square, and the numerator is nothing but delta 2 y0. So, this is nothing but y delta 2 y0 by factorial 2 into h square. This is the value of a2. In general, a n equal to del n y0 by factorial n h to the power n. So, using this technique we obtain all the values of the constant a0, a1, a2, a3 up to an. So, by putting all these values of the constant to the equation 1, we obtain this equation, the equation number 2. Note that phi x equal to y0 plus x minus x0 into delta y0 by h plus x minus x0 into x minus x1 into delta 2 y0 by factorial 2 into h square, and so on. And last term contains x minus x0, x minus x1 up to x minus x n minus 1, these factors, into del n y0 by factorial n h to the power n. So, note that the first term is a constant, second term is a linear polynomial, third term is a second degree polynomial, and last term is the nth degree polynomial. So, after simplification we get a polynomial of degree n using this method, and this polynomial is known as Newton's forward difference interpolation polynomial. But this expression can be simplified by using a new variable, unitless variable. That one is explained in the next slide. So, for simplification we use a new variable u, that one is defined as x equal to x0 plus uh. Since the arguments are equispaced, therefore, we can write xi equal to x0 plus ih. Therefore, x minus xi equal to u minus I into h, and this is true for all I equal to 0 to n. So, using this notation, the above expression reduces to this one, phi x equal to y0 plus uh into delta y0 by h plus into u minus 1 into h delta 2 y0 by factorial 2 into h square, and so on. Note that each term contain the same number of h in numerator and denominator. So, after cancelling all h, the entire expression reduces to y0 plus u delta y0 plus u into u minus 1 by factorial 2 delta 2 y0, and so on. So, this is the final expression for the Newton forward difference interpolating polynomial, where the variable u x minus x0 by h, and note that this variable has no dimension. So, this is finally Newton forward difference interpolation formula. But this polynomial also contains some error. That error can be determined by the following formula. We have seen that the error in interpolating polynomial in module 1 of chapter 2, and that one is Ex equal to x minus x0 into x minus x1 up to x minus xn, and into n plus 1 derivative of f at xi by factorial n plus 1. By substituting the variables x equal to x0 plus uh, this error becomes u into u minus 1 into u minus 2 up to u minus n into h to the power n plus 1 into f of n plus 1 at xi by factorial n plus 1, where xi lies between the maximum among the arguments and minimum among the arguments. So, this is the error in Newton's forward difference interpolating formula, but we can also replace the n plus 1 derivative of f by a forward difference operator. So, in terms of forward difference operator, the error terms is approximately equal to u into u minus 1 up to u minus n by factorial n plus 1 whole into delta power n plus 1 at y0. Now, we consider an example to illustrate the Newton forward difference interpolation method. So, here y equal to 2 by pi integration 0 to x e to the power minus x square dx. This is the probability integral function, and for different values of x we have the following table. Here 5 values of x are given and their corresponding values are also available, but our problem is to determine the value of y when the value of x is 0.456. So, for these given values we consider the forward difference table. The first column contains the values of x, second column contains the value of y, third column contains the first order differences. That means, the first value is the delta y0, second one is delta y1, and so on. And the fourth column contains the value of second order differences. That means, the first value of fourth column is delta 2 y0, next value is delta 2 y1, and the last value is delta 2 y2, and last column contains the value of third order differences. That means the first value is nothing but delta 3 y0. The red mark values are used in the formula, in the Newton forward difference interpolation formula. So, using this table of values, we can calculate the polynomial as follows. So, for this problem, x0 equal to 0.45, this is the first value of the table, and x is given, and which is equal to 0.456. So, in this case, the step length is h equal to 0.01, and hence u equal to x minus x0 by h, this is equal to 0.6. So, with this value and the differences mentioned in earlier slide, the value of y at the point 0.456 is equal to y0 plus u delta y0 plus u into u minus 1 by factorial 2 into delta 2 y0 plus u into u minus 1 into u minus 2 by factorial 3 into delta 3 y0. So, substituting all the values of y, y0, delta y0 and so on, after simplification we obtain the value of y as 0.479494, and hence finally the value of y at this point is 0.479494, the correct up to 6 decimal places. So, one important observation is that for Newton forward interpolation formula, in general Newton forward formula is used to compute the approximate value of the function f(x) or approximate value of y when the value of x is near to x0. This is the main criteria of Newton's forward interpolation formula. But if the value of x is at the end of the table, then this formula gives more error. The formula may be used, but the formula gives more error. So, in this case, there is another method known as Newton backward formula, which is discussed in the next slide. Now, let us discuss Newton's backward difference interpolation formula. In this case, the problem is similar to previous one. A set of values of x and y is given in a tabular form. Here also the arguments are equispaced, that means xi equal to x0 plus ih for all I. The problem is find the value of y when the value of x equal to x dash is at the end of the table. That means x dash is near to xn, that one mentioned by red color. So, in this case we considered the phi x in the following manner: phi x equal to a0 plus a1 into x minus xn. That means the last argument xn is entered first, plus a2 into x minus xn into x minus xn minus 1. That means the polynomial is constructed from the back side of the table. That is why it is called the backward formula, and so on. The last term is an into x minus xn into x minus xn minus 1 up to x minus x1. Note that a0 is the constant term, a1 into x minus x1 is a linear polynomial, third term is a second degree polynomial, and last term is the n degree polynomial. So, phi x is finally a polynomial of degree n, and the values of a0, a1, a2 up to an are determined using the condition yi equal to phi xi for all I equal to 0 to n. To find the values of ai, we substitute x equal to xn, then we substitute x equal to xn minus 1, and lastly we substitute x equal to x1. For x equal to xn, we have phi xn equal to a0, that is a0 equal to yn. Now, when x equal to xn minus 1, then phi xn minus 1 equal to a0 plus a1 into xn minus 1 minus xn, that is yn minus 1, this is equal to phi at xn minus 1 equal to yn, this is the value of a0 plus a1 into minus h, because a1 is multiplied by xn minus 1 minus xn. So, this is nothing but minus h. So, a1 equal to yn minus 1 by h, and this is nothing but nabla yn by h, where nabla is the backward difference operator. when x equal to x n minus 2, phi of x n minus 2 equal to y n plus y n minus 1 by h into minus twice h plus a2 into minus twice h into minus h. After simplification, we get a2 equal to nabla to yn by factorial 2 into h square. So, in general we can shown that ak equal to nabla k yn by factorial k into h to the power k. This is true for all k equal to 0 to n. So, using these values, the polynomial phi x becomes phi x equal to yn plus x minus x n into nabla yn by h and so on. Here also this expression can be simplified by using a suitable variable. So, that one is discussed in next slide. Here we use the new variable v, this one also unitless variable, where x equal to x n plus v h, and since the arguments are equispaced, therefore x I equal to x 0 plus I h, and also x equal to x n plus v h. Therefore, x minus x n minus I equal to v plus I into h, and this is true for all I equal to 0 to n. So, using this result or using these values, the polynomial phi x becomes this expression. Here also note that the number of h in numerator and denominator in each term are equal. So, after cancelling h, we get the last expression yn plus v nabla yn plus v plus into v plus 1 by factorial 2 into nabla 2 yn and so on. Here also seen that the first term is a constant term, second term is a polynomial in v of order 1, third term is a polynomial of degree 2 and so on. The last term is a polynomial of degree n, and this formula is known as Newton backward or Newton-Gregory backward interpolation formula. Like Newton forward difference interpolation formula, we can calculate the errors in Newton's backward interpolation formula. That error is also determined from the general formula for the errors. That one is discussed in module 1 of chapter 2. That one is Ex equal to x minus xn into x minus xn minus 1 and so on, and last term is the n plus 1 derivative of f at xi whole divided by factorial n plus 1, and after substitution of the variable or after introduction of the variable v, this expression reduces to v into v plus 1 into v plus 2 up to v plus n into h to the power n plus 1 into n plus 1 derivative of f at xi by factorial n plus 1, where xi lies between the minimum and maximum among the arguments and x. Now, let us explain this formula, that means the Newton backward interpolation formula, by considering an example. Here a table of values is given. This table contains the value of x and f x. The problem is to find the value of f when x equal to 0.48. Note that the 0.48 is at the end of the table. So, for this table of values, we calculate backward difference table, and the first column contains the values of x, second one contains the values of f x, third column represents the first order backward differences, fourth column represents the second order backward differences and so on. Here the red mark values are used in the backward interpolation formulas. So, in this problem the last value is x n equal to 0.50, x equal to 0.48, that one given, and we see that h equal to 0.05. So, v equal to x minus x n by h, and after simplification this becomes minus 0.4. Thus, by Newton backward interpolation formula, f at 0.48 equal to f of x n plus v nabla f of x n plus v into v plus 1 by factorial 2 delta 2 f of x n and so on. So, we substitute the values of f of x n, nabla f of x n, nabla 2 f of x n, and the values of v, we obtain phi or f of 0.48 equal to 3.43416, and this is approximately equal to 3.4342, correct up to 4 decimal places or 5 significant figures. Thus, the approximate value of A at 0.48 equal to 3.4342. Now, I would like to mention one important observation. The Newton's backward difference interpolation formula is used to compute the value of f(x) when x is near to xn, that means x is end of the table. And other observation is, if a problem is solved by Newton forward formula, that means Newton forward interpolation formula, then this problem can also be solved by Newton's backward interpolation formula by reversing the table. So, this is the very important observation of Newton backward and forward interpolation formula. We have discussed two important interpolating method. One is Newton backward interpolation formula and other is Newton forward interpolation formula, and in this formula we assume that the arguments are equal spaced. Now, we discuss another important interpolating polynomial, that one known as Newton divided difference interpolation formula or Newton fundamental interpolation formula, but in this formula the argument may or may not be equal spaced, and this formula is used to derive the other interpolating formula such as Newton forward interpolation formula, Newton backward interpolation formula, and also the Lagrange interpolation formula. Now, we define divided differences which are used to develop the Newton divided difference interpolation formula. We assume that xi yi, where yi equal to f of xi are given, and we define different order of divided differences. First, we define the zeroth order divided difference. The zeroth order divided difference for the argument x0 is denoted by f x0 within square bracket. Some author uses the parenthesis to represent the divided differences, and it is defined by f at x0 equal to f of x0. And first order divided differences is defined by f of x0 x1 within square bracket equal to f of x0 minus f of x1 by x0 minus x1. That means, the first order divided difference is defined for two arguments, and in general for the argument xi and xj, the first order divided difference is f of xi comma xj within square bracket, which is equal to f of xi minus f of xj by xi minus xj. This is true for all xi and xj, but I not equal to j. For three arguments x0, x1, x2, we can define second order divided differences. The f of x0, x1, x2 within square bracket equal to f of x0, x1 within square bracket. That means, this is the first order divided difference for the argument x0 and x1 minus divided difference for the argument x1 and x2 whole divided by x0 minus x2. And in general for three arguments xi, xj, xk, the second order divided difference is defined as the first order divided difference between the argument xi and xj minus first order divided difference between the argument xj and xk, and whole things is divided by xi minus xk. In general, the nth order divided differences is defined for n plus 1 argument as the divided difference for n plus 1 argument f of x0, x1, x2, xn within the square bracket equal to the n minus 1 order divided difference for the argument x0 to xn minus 1 minus n order divided difference of the argument x1 to xn whole divided by x0 minus xn. So, using this definition we can generate all order divided differences, and these are used in the next slide. But the divided differences are also valid for equal arguments. In previous slide we have defined the divided difference for different arguments, but here we shall define the divided difference for the equal arguments, and for two arguments x0 and x0 the divided difference is defined as limit epsilon tends to 0 f of x0 comma x0 plus epsilon within square bracket. That means, this is the first order divided difference for the argument x0 and x0 plus epsilon, where epsilon is very small. According to definition, this becomes limit epsilon tends to 0 f of x0 plus epsilon minus f of x0 whole divided by epsilon, and this is nothing but the derivative of f at the point x0. That means, the first order divided difference for equal argument is the first order derivative of the function f at the argument x0. Similarly, for 3 equal arguments x0, 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 the second order divided difference is equal to the second order derivative of f at the point x0 by factorial 2, and for 4 arguments the third order divided difference equal to third derivative of f at x0 by factorial 3, and in general for k plus 1 argument the kth order divided difference is equal to kth order derivative of f at x0 whole divided by factorial k, and by conversely we can write derivative, the kth order derivative of f at x0 is equal to factorial k into divided difference for the k plus 1 arguments, equal arguments. So, this result is used to develop the next interpolating polynomial. The divided difference also satisfied very important or interesting properties. The first one is divided difference is of a constant is 0. It is obvious from the definition. Divided difference of c into fx, where c is a constant, and that one is given by gx equal to c of fx. Then the first order divided difference of g is equal to c into first order divided difference of f at the same argument x0 and x1. Divided difference is linear. That means, if fx equal to a into px plus b into qx, then the first order divided difference of f is equal to a into first order divided difference of p plus b into first order divided difference of q. So, this indicates that the divided difference is linear operator. Also, divided differences are symmetric, all other divided differences are symmetric. And lastly, for equispace argument, the divided difference can be expressed in terms of forward differences. That is, for n plus 1 argument, the kth order divided difference is equal to 1 by h to the power n factorial n into delta to the power n y0. Also, we have proved that in the text the nth order divided difference of a polynomial of degree n is constant. Now, we come to develop or derive the Newton's fundamental interpolation formula. This formula is also known as Newton divided difference interpolation formula. In this case also we assume that the argument x0, x1 and xn are given, and we assume that yi equal to f of xi for all I, and it is important to mention that in this formula the arguments are not necessarily equispaced. Now, the first order divided difference for the argument x0 and x is f of x0 comma x within square bracket, that one equal to fx minus f of x0 by x minus x0, and this expression can be written as f of x equal to f of x0 plus x minus x0 into f of x0 comma x within square bracket. And for the 3 arguments x0, x1 and x, the divided difference is f of square bracket x0, x1, x equal to divided difference of x0 and x1 minus divided difference of x0 and x whole divided by x1 minus x. So, after rewriting this expression, we have f of x0 comma x within square bracket equal to divided difference of x0 and x1 plus x into x1 into divided difference for the argument x0, x1 and x. So, the first term can be written as f of x minus f of x0 by x minus x0, and the right hand side remains unchanged. After simplification, this expression reduces to f x equal to f of x 0 plus x minus x 0 into first order divided difference between x 0 and x 1 plus x minus x 0 into x minus x 1 into second order divided difference for the argument x 0, x 1 and x. Now, for the 4 arguments x 0, x 1, x 2 and x, we obtain f x equal to f of x 0 plus x minus x 0 into first order divided difference plus x minus x 0 into x minus x 1 into second order difference divided difference plus x minus x 0, x minus x 1 into x minus x 2 into third order divided difference. So, in this way, for the arguments x 0, x 1 up to x n and x, we get f x equal to f of x 0 plus x minus x 0 into first order divided difference for the argument x 0, x 1 and so on, and the last term is x minus x 0, x minus x 1 up to x minus x n into divided difference for the argument x 0 to x n and x. So, this formula is called, or this polynomial is called, the Newton's fundamental or Newton general interpolation formula. But the last term actually marked in red color, this one represents the error occurs in this interpolation. So, the importance of this formula is that we simultaneously deduce the interpolation formula as well as the error terms. Like forward difference table and backward difference table, there is a divided difference table, and in this table there are two sides. The left hand side actually determines the different differences between the arguments, and right hand side actually determines the different divided differences. The first column of the right hand side represents the value of the functions at different arguments, and the second column of right hand side represents the first order divided difference, and third column represents the second order divided difference, and last, that means the fourth column represents the third order divided difference. Similarly, the left hand side, in the left hand side, the first column represents the values of x and other column represents the difference between the arguments. We have deduced that the error term for this formula is x minus x 0, x minus x 1 up to x minus x n into the divided difference for the argument x 0 to x n and x. So, using the equation 9 of this module, we have shown that the divided difference of the argument x 0 to x n and x is nothing but the n plus 1 order derivative of f at the point xi whole divided by factorial n plus 1, where xi lies between the maximum and minimum value of the arguments and x. So, this is the error for Newton's fundamental interpolation formula. Now, we consider one example to illustrate this method, the Newton's divided difference interpolation method. So, here x and f x are given in this table. We have to calculate the value of f at the point 1.2. Note that the arguments are not equispaced. So, for this table of values, we constructed the divided difference table as follows. The red mark values are used in the formula. So, different order divided difference are mentioned in this table, and also the different differences of the arguments are mentioned in the left side of the table. In this case, x equal to 1.2, this one given, and the first value of the table is x 0, that one is x 0, and last value of the table is 11, that one is taken as x 4. The first order or zeroth order divided difference is 2.154, this one is calculated or shown in the previous table, and f of x 0 x 1 equal to 0.8610 and so on. Now, by Newton divided difference formula, the value of f at 1.2 is equal to this one, that means the zeroth order divided difference plus x minus x 0 into first order divided difference and so on. So, by substituting the values of all order divided difference and the values of x 0 and x, we finally obtain the value of f at 1.2 equal to 3.4834. That means the approximate value of f at the point 1.2 is equal to 3.4834, and this one correct up to 4 decimal places. So, in this module we have discussed 3 important interpolation methods. One is Newton forward interpolation method, second one is Newton backward interpolation method, and third one is Newton fundamental interpolation method. The third method is theoretically very important, because from this formula we can derive the other formulas such as Newton forward formula, Newton backward formula, and Lagrange interpolation formula. All these derivations are available in the text, but one important observation is that if we add one point at the end of the table, either at the beginning of the table or at the end of the table, then the previous calculation are useful for this formula, for this Newton's formula, but this is not applicable for Lagrange interpolation method. In Lagrange interpolation method, the fresh calculations are required to compute the entire interpolating polynomial.